pre-calc, I was thinking about this for a long time. I was like, you cannot, like, complex numbers cannot possibly be defined under 2 planes. Like, if you're talking about, like, real-wise. It just doesn't make sense.
Well,
But if you have two, because the only way you could show it visually is if you had 3 planes. Because then you could have something that dips under to hit a -1. Because, you know.
oh, this is the 3 planes you mean, like this one, that one.
And then the one sticking out.
One sticking out. Oh, I see now. Okay, so I got it. But my point is that this idea that, oh, it's just, you know, it's out of the board. Well, you're not really talking about original function anymore. Right now you're talking about a corresponding function.
Yeah.
You're talking about z equals to f of x comma y, right?
Yes.
And still not even really that. That's still a lie.
Yeah, I'm not really talking about fx.
Because
I'm talking about a function of x, y, and z, really.
well, let's call this g of x, right?
Yeah.
So f of x comma y is like, it is g of x plus iy,
Yeah.
right? And that's still not the truth, because if you want z to be a real axis, obviously this isn't going to work. That's complex.
Yeah.
Right? So really, this is still not quite it. Z is equal to the real part of g of x plus iy. See, it's the real part in this case of. So for this one, you know, x squared. If we put x plus iy squared. Is that right?
Mm-hmm.
And so you get like x squared plus 1 minus y squared plus I times 2xy. So this thing they're talking about is actually z equals to x squared minus y squared plus 1. That's the actual graph that these folks say, quote unquote, make sense of complex numbers.
See, but my problem with the two-dimensional description of the complex plane, you know, where you have a C and a real, like, we know that R is a subset of C, right? But if you have C cross R, you don't, real functions don't really exist.
C cross R?
Yeah, so this is how most people explain the complex plane. But you
Well, I
know,
would say that the top is not C, it's IR. It's the imaginary axis, right? I mean,
yeah, you say that. Well, I guess if you have 2 points, it would work. You know, because you could have R comma IR, and then you know you write it.
Right, really, I mean, I would say C is the direct sum of R and IR. Again, it's the assumption that 1 and I are linearly independent.
My problem is that I don't know. I just feel like for a true complex number, you should be able to put I wherever you want. Like if.
Oh. Well, yeah, I mean, this is the whole concept of this plane is looking at the real substructure of the complex numbers.
Yeah.
So I think in some sense you're right. It's not.
So it's because we're talking about imagining it, but
If you just,
we're restricting it to a subset too.
I mean, if you multiply that, you multiply complex numbers together, there's like, you multiply their magnitudes, and the standard angle of the product is the sum of the standard angles of the numbers multiplied, you know?
Yeah.
But getting back to the problem, so like this, if I want to visualize what is, you know, the z squared plus 1 function,
Mm-hmm.
right? The z squared plus 1 function, a partial story is told by looking at the 3-dimensional graph of x squared minus y squared plus 1.
Yeah.
But I really don't know, I haven't seen much of anybody actually doing that. It's something we put in cool YouTube videos, but it's not something that I've actually seen people use.
Just, I don't know, it might just be my quarrels. It's just because we're talking about like imagining how things would look by restricting it. Like if I told you to imagine a sphere, but I told you to imagine a sphere in 2 planes, you'd see a circle, not a sphere.
Right.
So I think that's the inherent problem with complex numbers too. We're trying to imagine something that we're restricting to a subset.
Right. Well, I think that the basic problem with visualization of like complex functions is that if we try to use our usual way of looking at things, there's too many dimensions to do it directly.
Yeah.
So typically we look at, all right, so like a function of, the first thing we start is like graphs of functions, right?
Mm-hmm.
So graph of functions, you can let the x-axis be the inputs and the y-axis be the outputs.
Yeah.
And then you get simple statements like the graph has to satisfy the vertical line test because each input can only go to one output, right?
Yeah.
Or then you can also look at level sets of equations. You can say f of x comma y equal to constant, and at least locally you can express that as like the graph of a function.
Yeah.
Although it might be a function of y if you're like on one of these kind of things. But anyway, the point is we're dealing with functions of a real value function of a real variable, then the plane works, right? And then when we shift gears in Calc 3, we have functions of 2 real variables, but we can still get away with 3 dimensions to visualize it because z equals f of x, y, you can visualize that, right?
Yeah.
And, but once you get to 3 variables, if you got like w is equal to f of x, y, z, that's not something you can directly visualize in 3 dimensions, right? You need a 4th dimension to out.
Yeah.
You need 3 dimensions for the inputs, you need a 4th dimension for the outputs if you're going to keep doing the same thing, the same ways. So the way to get around that, of course, is you can look at like, you can do like colors, you can graph all of the outputs which have like level 1 is the same color, and then all the outputs which have, level, and you can play that game. So for a function of a complex variable, you're talking about a mapping from C to C. And so like directly speaking, there's 4 things going on there, right? So you'd kind of need a 4-dimensional space where 2 of those are being understood as inputs and 2 of those are being understood as outputs.
Yeah.
But in practice, like nobody can really, you say you want to visualize a complex function in that way, you don't really gain anything from it because people don't have the ability to visualize in 4 dimensions, at least not directly, most people. So what do?
You have to restrict it, of course, but...
No, we don't restrict. What we do is we visualize the input and the output separately, and we understand it in terms of a mapping. And then you analyze how the map carries different shapes from one plane to the other.
Okay.
So like, try your eraser. And there are lots of websites like this. Let me try to give an example of this idea I'm talking about. So like, we'll look at a relatively simple function, f of z equal to 1 over z. Right? So here, you think of this as being equal to quote unquote w. And what you want to think about is like here's the z plane, and the f maps over here to the w plane. Now, this strategy allows you to visualize things. You can even visualize something going from like a 3-dimensional space to a 3-dimensional space using this technique. Past that, you're still stuck. But, okay. So the question is, what happens to certain canonical shapes in here how do they map over to there, right?
Mhm.
So z, if we look at z is equal to r e to the I theta, that's the polar form of a complex number. You notice that f of e to the I theta equals 1 over e to the I theta, right, is equal to e to the minus I theta. So if I say that this is equal to like s e to the I beta, so I'm using polar coordinates s and beta over there. So here I've got r theta polars. Over here I'm going to say I have s beta polars. Then what happens is this is the parameterization of the unit circle. So the unit circle, a point on the unit circle, gets mapped to a point on, oh, well, here s equals to 1 apparently, right? Beta is equal to minus theta. So we have a counterclockwise oriented circle here, right? That's the standard e to the I theta goes counterclockwise, like so. And what happens? It gets mapped to the clockwise unit circle over there. And then rinse and repeat. So like what happens, for example, to the circle of radius 2 over here? It gets mapped to the, so this 1/2 e to the minus I theta, right? So we started out with radius 2 over here.
And we end up with half a radius over there.
So it mapped from this circle to this circle in here.
So,
And one more. And if we look at the circle of radius 1/2 in here, what happens?
because it would go to this radius of 2.
Mm-hmm. And again, the so what it's doing, this mapping, is it's taking the inside of the unit circle and it's flipping it inside out. And it's taking everything outside of the unit circle and flipping it in. And then you can also study, like, to gain a little bit more appreciation, you could study like a line. What happens to a line, like let's say, this line through the origin like that.
It would reflect it across the y-axis.
Yeah, I guess I should come up with a parameterization for the line, something like z equals to what? Z equals to some complex number,
Yeah.
c times t, right? Without loss of generality, you could say c e to the I theta times t. That would put this thing at angle theta. And then so if you look at f of e to the I theta times t, what happens?
Actually, t stays the same, but just the e to the I theta that changes. Ooh.
Yeah, t stays the same. I mean, you're right. I mean, well, not quite. I mean, it flips it.
Yeah.
And
Ooh, the inverse of it, yeah.
see that gets a little bit.
Yeah, because in a more general sense, like it would take a parabola and it wouldn't like flip it anyway. It would make it like instead like that.
Yeah. Oh, that's the other thing. We could look at what happens to parabolas.
Yeah. No, I mean this is the same thing that's happening here. You get instead of going this way, it's gonna veer off more.
Oh no, it's still along a line.
Yeah, but it's not the same slope. Slope
No,
changes.
well, yes, different slope. This one's at angle minus theta.
Yeah.
So this is a line at angle minus theta.
Mhm.
But notice it's a little bit complicated. The points at infinity for this thing,
Mhm.
they flip back to 0, right?
Oh yeah.
Like infinity has gone to 0 here, and 0, right? Technically speaking, this point, it depends on how you want to look at things, but if we're just working with complex numbers and not infinity,
Yeah.
there is a way to extend the complex numbers to infinity in such a way that the arithmetic is consistent. But setting that aside, the domain of this should exclude the origin, right? Because
Yeah.
division by 0 not defined. So, but as you approach that point, you're making this arbitrarily large, right?
Yeah.
So if this is at theta, like minus, it's down here, right?
Yeah. No, I don't even think it's like a direct reflection either.
Right. So it's this one's at theta, this one's at minus theta.
Yeah, but the magnitude.
They are.
Magnitude would change it.
That is true. If I was to track points, it's complicated.
Yeah.
But this much we can say.
It's in that quadrant for sure.
And the orientation, it never actually gets to 0 in some sense.
Yeah.
And it approaches 0, but to actually get to actual 0, well.
No, I think it would have. I think you could get to
if I let
0.
If I let t go to infinity, actually reach infinity,
Yeah.
whatever that means, it would get to 0. But if I don't, it just approaches 0. But the larger point is, it approaches like,
Yeah.
it's as t increases, this gets smaller and smaller and smaller. So,
Yeah. Back to
this is how we visualize complex functions. But not just this, like what people will do is they'll look at like a grid in the domain and then see what happens to it. What does it look like? How does the grid get like mangled by the mapping?
why don't we? So you're like, this is a really oddball idea, but remember when? Did you ever read? Or like I didn't read it, but like I have a general understanding of the Brownian motion from Einstein.
I mean, I know what it is, but I've never read that book now.
Okay, so essentially the thing is he restricted it to one dimension, and that's how he proved it.
Mm-hmm.
Why don't we do the same thing? Like we have a function with X amount of outputs, but we restrict inputs to one plane, and then we do it for everyone. So like, if we have a function of X, Y, Z, we look at only the outputs in X, and then only outputs in Y, only outputs in Z, and then we combine all those things and see what it makes.
I think basically because if you look at the inputs separately, then you lose track of how the joint action of the two inputs comes together to do things.
No, but that's my point. Like, that's why you. I don't know. Maybe I. Like, so your inputs would still be three-dimensional, but you're only looking at the outputs of one dimension. And you construct it that way. You look at every single thing. You look at every single dimension that you had of variables, and you look at all of them to see a broad picture of what was happening in each. So like, like if you have like a helix, on an XY plane it's going to look like a circle. On a Z plane it's going to look like this like little wobbly thing, a ZY plane. And then on the XZ plane it's going to look like a sine graph. Or no, I think the YZ plane looks like a cosine graph, the XZ plane looks like a sine graph. And then the XY plane looks like a circle. But if you look at all three of them, it's helicoid. That's what I was trying to say. I see the inherent problem with that though, because you'd have to be able to picture that, like stick it together. But
I feel like, for a function where you have two inputs and two outputs in the real sense, the question is how are you going to, what planes are you talking about? I mean, I don't.
Well, for the helicoid example, like in 3 dimensions, we have two outputs, or two inputs, and we have a plane on Z,
I would argue that the helicoid or helix?
It's the one that's cosine sine 1, and it just is literally just like a...
Is it a surface or is it a curve?
It's a curve.
Then I would argue that the inputs, well, it depends on what we mean. If you're thinking about it explicitly, it's the map. That's a mapping from R to R3. Or if you want it to be,
It is open, but we're getting closer. Sorry.
what do you got to? What's it? What we got here?
I'm getting 100 points per day, so that we get to go for
How about you get 200 points? I mean, that's a good start, but you do more. If we get to Gokunin, we can get 200 Shinobyte.
Ooh.
But he's just been getting to tier 2 Chonin, which only gets us 160 Shinobyte. Yeah, 200 Shinobyte would be better, because then we can get more of the fancy new cards, which of course are only like useful for a month, and then they've got new cards that, you know.
Yeah.
I mean, if I was just to like get off my butt and spend $300 a month on the game, then we could be really awesome, but...
Oh, well, see,
I'm like, while you're doing that, see if I can find a website that does what we're doing right now.
this is horrible.
Mm-hmm. No, I totally see what you're saying there. I just don't know.
And then, thinking.
Right. Oh yeah. Hey, and so what I'm in the middle of trying to explain to you is a potential method for visualizing hyperbolic maps.
Yeah, but this is the method I'm thinking. If you took a hyperbolic map and just broke it down into parts in the real sense.
Yeah, but if you, I mean, so I'm going to show you. I'm in the middle of showing you a way. If you can find another way that's based on like this idea, I'm all for it. See, because the thing is, direct visualization is not possible if we're just going to like naively generalize the idea of graph. We can't do it because it's 4-dimensional, right?
Yeah.
So there are a lot of different ways you could go. I mean, if you can think of a way to, so you maybe would be thinking, so I've got,
The only bad thing would be for every n-dimensional, like if you got the 4 dimensions, you have to break it into 3-dimensional outputs. Like, I forgot. It'd be you know the combination thing, the like 4CR or 4C NCR stuff. You'd essentially have that type of thing going on, where like if you have combinations of 3-dimensional graphs, then you have to, every time you get a 3-dimension, then you have to break it down into 2-dimensional parts. So like this thing becomes really nasty quick. Especially when you're talking about very big numbers.
yeah.
So like I think for 4 dimensions you could map it.
You know, I used to have a number of complex function visualization websites on my link to my website,
Yeah.
but they're gone now. And I think what happened was a lot of them got killed in the stupid Java issue. A lot of them were Java based, and like there was some kind of
Anyway. Yeah, the combinations of 4 dimension, I think you get like 24 graphs. I'm thinking of it right. Like 24 2-dimensional graphs.
Mm-hmm.
So that inherently shows a problem right there. Because I think okay, this is it.
Okay, so
Yeah, I'm right. Because what I'm saying is that this is a probability thing.
what I'm,
If you have a 3-dimension, how many possible ways can you show 2-dimensional stuff? And so 3, C2, that's 3. You can show 3 ways. I showed it there. But if you'd have to do this for a 4-dimensional. How many times can you show it in 3-dimensional? And then you do it again. So you start doing a mess of stuff. what I'm saying is like your two-dimensional graphs you're gonna have a lot of two-dimensional graphs just for 4 dimensions, and then 5, and 6, and 7. Because you'd have to keep breaking them down. You take a 4-dimensional thing and look at every single possibility of 3-dimensional graphs, and you take all those 3-dimensional graphs and look at every possibility of 2-dimensional graphs. And so you just have a whole bunch of graphs, and so it gets pretty nasty.
For me, I mean, some people are like, for them, visualization just means that they can find some picture and then it makes cool, pretty pictures with their, various, computer algebra software, and like that's enough for them. That's not enough for me. To me, a visualization is only as useful as you can actually have an explicit understanding of how it connects with the original problem you're visualizing.
Mm-hmm.
So when it's obscured, like the thing I started talking to you about, they're like, oh look, it just comes out of the page. But they never told me an equation. They never explained clearly what they're doing with the original function to get to the complex function, which changes 1 to 0.
They're just showing you a pretty picture.
To me, it's nothing more than mathematical snake oil. Like it'll convince a lay audience who doesn't know what's going on that they've done something, but in reality, they don't really explain what they're doing in that video series until like the 10th video. They finally get around to explaining, oh, we're actually, extending it to x plus iy, and we're taking the real part, just looking at the real part of it. But it's the same as you just take the graph out of the paper and just rotate it around. It's like, what does that even mean? That's not a valid mathematical thing that you can do to a graph. I mean, it is something you can do to a graph, but
it doesn't tell you anything about the original problem.
I could also take the original graph and go like this.
Yeah.
and any thousand of other things.
I think that's where this could help.
This is just part of my own personal like.
You have like a valid point.
It strikes to a deeper point, which is just that I don't respect salespeople. And that this.
Well, with this, what you do is what you don't lose is that what you're talking about. It's just what you lose is a cool visualization. But I don't know. So how I describe this essentially is we can visualize things in 3 planes and curves and whatnot. But I'm gonna get real funky here.
Mm-hmm.
If you take planes of any n-dimensional thing, you can make a sphere of planes. And will this get you anything? I have no idea. This is just me being wild. So like, and then you have something coming out towards you, and then going back, and then you have all these planes going out. Just think of any 3D thing, and you map all these graphs on like this plane, this plane, this plane, this plane, this plane. It might do something that you could possibly. What you don't lose, essentially what would happen is you would see everything in a 2-dimensional sense, but it would all be glued together.
But
and you could always take.
All right, just to give you a specific question, you've got a 5-dimensional thing.
Mm-hmm.
Trying to visualize. How do you choose the 5 axes on the sphere?
Mm-hmm. Oh, it wouldn't be 5 axes. Like I said, just a 4-dimensional is 24 axes.
How do you choose the 24 axes?
Oh, because you break it down conventionally. You have a 4-dimensional thing.
You're gonna choose them like symmetrically, like you assume. I mean, there's.
Yeah, you don't have to do that. If you have a 4-dimensional thing, how many combinations of this can you get 3 dimensions from? That's.
Oh sure.
And then how many from there can you get 2 dimensions of? And then you match, and you plug it in that sphere.
The XYZ sphere.
It'd essentially be an XYZ sphere, but you'd have a lot of axes. Like you choose specific axes that pump out, and it would always, since these are always going to be even numbers, just because of how factorials work, it would always be symmetric. It could always be symmetric.
You can always choose like antipodal axes.
Mm-hmm.
Yeah.
This is a radical idea. I mean, literally. All you'd be able to do is see everything, especially depending on what program you do. You would see every graph interacting with each other. You wouldn't see anything 5th dimensional. You would just see a 3-dimensional representation of it.
How do you get something from the,
Here, I'll explain it using.
How do you get how do you get something on this? Like, what are you, from each projected graph, what are you, from each projected graph, what are you getting on the circle from that projected graph? Like,
so take a fifth dimensional thing and we break it down like how I broke down this three-dimensional thing. You can see three-dimensionally like xy is obviously this, and yz is obviously this, and then xz is that. What you would do is you'd start connecting even more planes around. So like these are just 3 planes, but I mean you can add more planes. I mean you could go here and then that way, and so you'd have a negative z xy plane, like with the line that's going through xy, like xy equal to x on this plane, and so you have a plane like going diagonally that way. And so you could write a graph going.
and from that graph, what would you put? Now, would you be putting something on a sphere from that in your visualization?
So the sphere, like this all a sphere. I mean like essentially like this whole thing's a sphere, and like these are just radiuses. Like all these points are just radiuses. And so what I'm saying is that if you have a good computer program that can map all these things, what you'd be able to see is like the interplay between everything. Because while you wouldn't be able to see in 5 dimensions, you can have a 3-dimensional representation where you take specific axes and you put them all together. So like this is very. I can see. I wish I could just like project it on my head, but essentially like you have all these planes, just all these planes like encapsulated into a radius of things. So you can make that radius whatever you want depending on what you're restricting on, like what points that you want to look at in these things. It would not get you anything 5th dimensional. It would just show you specifically where points match up.
I mean, I'm envisioning you'd have different colors or something for the different choices of axes, and then what I'm unclear on is like once you pick that axis on your sphere to represent the particular plane restriction you're looking at or whatever, that gives you like a curve on the sphere corresponding to the curve in the plane.
Yeah.
And you're just going to like color those different colors on the sphere so you can look all of.
Yeah, and like
kind of see all of the.
Yeah, and like depending on how you rotate the sphere, you would get different things.
Like maybe you'd see like the circle, see the sine and the cosine.
Yeah, and then like you know if you could like, and then like if you zoomed out, you'd be able to see some interplay between these graphs. And it would not get you anything 5th dimensional. All it would do is show you a 3-dimensional representation. Like I said, it essentially like you could start putting things together. Like you know, like if I have a 5th dimensional equation and I want to see why these outcomes are these outcomes geometrically, you would be able to see a sort of geometric representation of it. It would not be pretty by any means. You would just be able to see something of what these interplaying things are, and that's my best bet. That's my best idea that I have. Is it a good idea? I have no idea. I'd have to do it and make a program for it, or use a program that's already in play.
Or I would say before a program, just come up with like a specific example that's sufficiently simple that you can actually graph the things.
Yeah, just like I said, the problem I feel like I'm going to run into.
I would need to see an example.
Yeah.
To better understand your idea, but you know. Oh, if you look at your computer, and by the way, this is like, it's fine to be fuzzy to start with.
Yeah.
That's exactly the kind of like madcap, you know. Visualization it's an open thing, right? There's not just one. You know, it's kind of like, where do you hang a painting on the wall? I mean, I don't know. Or,
yeah. No, the worst thing about visualization
choosing the lighting.
Yeah. The worst thing about visualization for me is that people don't remember that we only see 2 points in 2D.
Well, okay, so that gets back to my my real point to you, which is I prefer 2-dimensional visualization, which is why I'm fond of this viewpoint.
Yeah.
Because while we're dealing with really 4 dimensions, 2 input, 2 output, we can, you know, everything that we're looking at is concretely 2-dimensional. And so if you look at the link I sent you,
yeah, I'm on it.
and you go down to using conformal maps.
It's just like an electromagnetic system.
It does look like that. See there, you see. So we're at newcalc.com/.
Yeah. I'm on.
Hang on. There are actually people watching these, believe it or not.
Oh, hello, people.
Yeah, hello people. Newcalc.
Oh,
In
yeah,
fact,
I see the
I got an
comments.
email about I have duplicated videos in our previous.
Oh yeah.
I need to go fix that.
I'll just comment on your stuff whenever I start looking at your abstracts.
Complex functions. Anyway, you'll figure it out.
Yeah.
I think it's just HTML, but anyway.
Yeah.
So in there, under the conformal maps, so he's looking at the exponential function.
Mhm.
And see, that's what the exponential function does if you like feed it a grid that's based at, where is that? Something like,
Yeah.
0.5 minus 0.3i.
Yeah.
It takes that little grid and it maps it to that sort of, I don't know what that thing is called, that sector in the
Are you still up here?
down,
You're talking about this thing?
down, further down. There you go. No,
This-
down further. Down further. There you go.
This.
Use it right there, yeah. Using conformal maps.
Okay. Oh.
See, I was illustrating this idea with some sample circles,
Yeah.
but a lot of people like to say, take a little grid and see what happens to it.
Oh, yeah. That's even. Yeah, I think that's.
And see, so you can start to get a sense of what the complex.
Geometrically, this is complex.
Look at that! Look at that!
Yeah.
And then he's got some snazzier stuff, like he's used color coding to map
apple
the.
logo.
See the apple?
Yeah.
That's pretty cool. So he the you see the square the gray shaded region outside the
Yeah.
apple is mapped to that, whatever you want to call that, and then
Oh.
the red strip maps to that red sector over there.
Yeah. That's kind of mind breaking, not gonna lie.
Uh-huh.
Because that's not intuitive.
So this was one of my ideas was to come up with a sort of a nice, and I have asked students to do this before who I feel like could have done this, and I don't know why they haven't done it yet, because I don't think I'm surprised that I haven't had a student do this yet, but like I'm interested to see a similar tool. This is not a tool, obviously this one isn't, right?
Yeah.
But you can easily see how you can make a tool where you're taking, like you have domain, you have range, you pick your hyperbolic function, and then you can track how various standard shapes get mapped under the hyperbolic function. And you could gain some insight as to like what the function's doing.
Oh my god.
But in terms of like the coding, I think we could pretty easily piggyback off some stuff my brother's done using Sage. We could build a Sage interaction and do this sort of thing.
Yeah. I am going to programming in the fall, so
Mm-hmm.
I'm sure I'm not gonna be able to do any of this, but I'll see what I learn. See, there's not a lot of programming in the CIS thing. That's what I was upset about.
Mm.
It's a whole bunch of hoopla.
Well, yes, there's always hoopla at the beginning of every major, unfortunately.
No, I looked at all the classes, like I literally only have to take programming one.
Oh.
Figured out CIS minor.
Oh, what are the other classes you take? But, by the way, that same website, it also has some other alternative three-dimensional visualizations.
Yeah,
Yeah,
that's what I was
there's-
doing at Losing Oz.
So there's, and each of those are looking at a different aspect of it, right?
Yeah.
In my humble view, each one of those is useless unless an explicit account is given as to what that picture means relative to the original equation.
Yeah.
And that's my pet peeve with all this stuff. Is like, oh, look at these pretty pictures. Like, where are the equations? Like, define what you're doing.
Yeah. I have to do programming 1, intro to CIS, network communication, system analysis, database management, system project management. That's it. Then I finish. So.
Okay. I think databases are important, right?
Yes.
Um,
Also, after I'm still gonna technically need another math elective, so that's funny. Because number 3 is only 3 credits, so
yeah.
I only have 12. So I'm gonna need 1 more credit.
I see.
But also, I technically have to still take biology, even though I took it, because it was. I don't know what biology I took for my thing. UW is weird. Anyway.
You should argue about that. You should waste your time doing biology. Sorry.
Oh no, I've already taken biology. That's the thing.
Right. So then you should take it again.
Yeah, no, I actually even took the same class. Like it's literally just it says 105 instead of 104, but it's the same class. Like we had the same lab.
So advising sent you to the wrong class?
If they did, it essentially mean they sent me to like college physics instead of technical physics, which would really suck.
Well, I don't know what to say about that.
I mean, I also took pre-cop and trig my first year when I didn't have to. But then again, I mean, some good things happened. I became a math major because of it.
Maybe I should just, maybe as a service to the university, I should be like a degree plan auditor. You just take, all right, like math department, this is important. We need to go through the however many new students, whether there can't be more than like a couple hundred, right?
A couple hundred what math?
Like
majors?
new students, like freshmen, like what, maybe 500?
Yeah, I'd say that.
So
that's a pretty good freshman class. Honestly.
I think you take a day, pick 4 or 5 math professors and say, all right, we're going to do. Let us find amongst these 500 students the ones that have been misplaced.
Yeah.
Because you know full well advising is like, they don't know, I mean, with regard to math.
I mean, they have to go through 500 kids. I mean, they're not going to look through what they did in high school. I mean, I wouldn't.
I don't know, I wish we could find people before they waste their whole semester. It's so expensive and always a problem. It's always been a problem.
Oh,
The other place that advising wasn't a problem for me was at my community college where my teacher did the advising for me. He was like, I'm like, 20 hours, isn't that a lot? He's like, oh, it's fine, you can do it.
Oh, no, the school capped me. They said I couldn't take over. I was at 19 and I wanted to take, I forgot what class I wanted to take, but they said no. They refused.
Yeah.
And also, not only that, I had to pay $500 to go over 18 credits.
Mm-hmm.
And I was just like, you guys suck. Like, in my wholehearted opinion, it is just so people don't graduate earlier and they have to pay tuition more semesters.
Very possibly. So.
Because like, if someone could realistically graduate in 3 years,
I mean, you can make
credits.
arguments on either side, like, oh, statistically, students who get overloaded, they don't do as well, blah, 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 but the fact of the matter is, person who seeks out an additional course of their own volition.
Oh, Racketers was like that. Racketers was told, like, he approved me for all these classes, and he was like, why not? I was like, why are they saying no? I was like, can you go talk to him? He was like, and he did, and he was like, nope, I said no. Because he was just like, yeah, if anyone was going to take him, like, you would be my first candidate to, like, and then why is college geometry on the mathematics thing? I would throw that class out.
It's in part of the required?
Yeah. See, look, it's a math elective.
A math elective?
Yeah.
Or a math requirement?
You have to do 16 credit hours of electives.
Oh, so you could do other things.
You could, but that was the only thing they were offering at the time.
Ah, well, hopefully we'll.
But like, I love Miss.
I mean, hopefully we'll have more things because I agree, but that course is not probably the right thing for graduate school bound math majors to take. I mean, it's.
Parker, what's her name?
Professor Parker's taken over for whoever was there before.
She was working out. She's a PhD student at Alabama. She was working here part time. She's blonde. Kate Pate. Is it Pate? Miss Pate?
You're
Something Pate.
Kaylee, yeah.
Something Pate.
I think Pate is right, but now you got me like.
Okay, but anyway, that I
I don't say her name enough to be like rock star.
like. I absolutely lost my mind in that class all the time.
She is a meticulous teacher,
No,
right?
actually,
like she is
systematic.
systematic, right?
As a person, I loved her. Like she was such a sweet person.
It's just
as a teacher, I was like, I'm losing my mind in this class. Are you really going over constructions right now?
That's what that class is. Yeah.
I was just like, are we? And I would do the
That is
homework.
that's what that class is.
And
yeah.
some of the homework was interesting. I would actually have more fun doing the homework than I would in class. But I was just like, this should be a 1 credit class. You should literally give us homework, like give us the PowerPoint, and then we just come in for the test.
I was telling Professor Parker, I'm like, well, if you ever miss a day in there, like let me come in. I want to talk to the students about like the hyperbolic and other geometries. Yeah.
Who's in that class? A lot of you've probably had all these people in your class. I promise you right now, they would not know a slick of what you're talking about. There's nothing, and I'm telling you, it felt like a high school class. I was losing my mind in that class.
Yeah,
I lose my mind in all the pointless classes.
See, that really should be a modern geometry course. I wonder, there may be a difference. I may be talking about two different courses right now.
No, the one Miss Parker, is it a guy or a girl?
Okay. I mean, girl. What am I talking about? Girl.
Okay, yeah, Miss Parker, if she's
Yeah.
teaching it now, I promise you right now, like, it's just constructions. Like, constructions, just,
It's supposed to be axiomatic Euclidean geometry. Yeah.
She went over, like, she mentioned Euclidean geometry, but I mean, like, it wasn't, I took that, and I thought, like, I took that, and then I was just like, oh, that's why I choose differential geometry. I was like, oh, I guess I should keep taking geometry. And then I looked up differential geometry, and I was just like, this is not the same. This is nowhere near the same thing. I literally went from, like, doing we were doing tessellations. That was one of our projects, is just draw a tessellation. And I was just like, and, like, by no means am I some Einstein genius here. I'm just someone that needs to be challenged. And I really felt, because I was in Physics 1, which I had taken as a senior in high school. I was in Physics 1, I was in that class, I was in Calc 3 Linear, and then, what else was I in? I was in something else. I was in something else. Anyway, but yeah, that class drove me insane.
But,
because I was like, I don't have to go to this class. It's just, I liked her, so I didn't want to be mean.
so if, this is something to keep in mind though, if you can,
I'm on profit stats, that's what I was in.
like this is a very, I think if you could do this, something similar to like what we're looking at, if you start looking online, you'll find some tools that actually have, where you can put in different complex functions and look at how they map standard grids.
So no one's done this for the hyperbolic numbers?
Not that I know of, no. So.
Well, there's
I
not
think-
as much
so there's-
literature on hyperbolic numbers either.
No, I don't think they're widely known or studied, but the
You can erase all that.
thing is, alright, so like, my brother said that there's a journal that if we write a paper that also has a corresponding like application, like computer app kind of thing, and publish in there. And so that, if we did some, low-level original stuff in the hyperbolic, it probably wouldn't be good enough to get into like, a super fancy tier whatever research. But if we also did the computer part, then that might be enough to qualify us for that journal. That's kind of a target we could shoot for. And there are other things about the visualization as they tie into the problem of conformal mapping. All right. that I'll tell you more about. But I guess we should finish this.
Yeah, let's finish the paper.
We're in level 5. So last time we have proved that, and really theorem 5.2 rests on the division algorithm for polynomials over an algebra, and in fact there is such a thing, you know, as I was telling you before I turned the camera on. We can divide. There is a division algorithm as long as we're dividing by a polynomial which has got a unit as the leading coefficient. We can systematically subtract off a higher order part of another polynomial and be left with a remainder which has lower order, which is ultimately all we need for the factor theorem to be true. So there is a factor theorem. Right, for f of x in the polynomials over the algebra if f of alpha equals to 0, then f of x is equal to x minus alpha times some g of x. Right? Now theorem 5.2 actually is a little bit sneakier than that. It tells us that, what did theorem 5.2 tell us? Theorem 5.2, if you have, so yeah, we're in the AODE's paper that I wrote with Nathan.
Yeah, I was just looking for that.
Nathan Bedell, who I need to give a phone call to. See what he's up to. All right. So we have L is an operator. So it's a polynomial operator in the differentiation. All right. Where big D is dd zeta. And that was supposed to be zeta. Oh well, my zetas and z's. I will eventually be better at writing zeta. Actually, it's not true. If it would have happened, it would have happened by now. So if this defines AODE, L of beta equals 0, right? What? Actually, I'm thinking of theorem 5.1. Sorry. I'll state theorem 5.2, but 5.1 was what I was thinking about. 5.2 in my opinion, is easier. If you have this and that, and if L is equal to d minus alpha times L prime, all right, where alpha is an element of A, then eta equals e to the alpha zeta solves. We call this thing star. So the theorem 5.1 was a statement that if so actually you put theorem 5.1 and 5.2 together, you get an if and only if. But so here the proof is pretty benign. So you're like, okay, so you have L of e to the, let's assume that everything is as stated up there, right? You take L of alpha zeta. Well, that's d minus alpha of L prime of e to the alpha zeta, right? But the thing is, these commute. I guess is that how I proved it? Oh, I I just say assume, observe the commute at the start, fine. So L prime, and then we can take d minus alpha and e to the alpha zeta. But this is 0. Because it's e to the alpha zeta minus alpha e to the alpha zeta. So it'd be alpha e to the alpha, words. So that's that. Which is L prime of 0, which is 0. Now, you could go through. I mean, if you're like you haven't proved that those operators commute. Fair enough. I guess I haven't. You know, you could just do a direct calculation just the same. So basically, you can show that L prime. If L prime is like g of d, it's a polynomial in the differentiation called g. Well, just direct calculation of L prime e to the alpha zeta gives you g of alpha e to the alpha zeta. So like the other way you could do this would be just straight up, you know, use this identity, you plug that in here. G of alpha is just a number, whatever it is, pull it out, and then you're back to here again. So you get g of alpha times 0, which is 0, so great.
Oh yeah, because you have to differentiate, yeah.
So it's basically the same arguments that you would use in a Calculus 2 class if you were discussing second order problems and pointing out that the exponential solves the problem as long as the argument for the exponential solves the characteristic equation for the problem. Of course, you don't need alpha to solve the characteristic equation for this problem. G of alpha doesn't have to be 0. The fact is you get
0 no matter.
You know, this becomes basically g of alpha times that if you go that path. So it's like this is 0, so you know, whatever. All right. So that's theorem 5.2. Theorem 5.1, which I'll remind you now. There it is. So backtracking here. Theorem 5.1 said that if we had, you know, L as above, so L is the differentiation, the polynomial in the differentiation operator, and L of e to the alpha zeta equals to 0, then there exists L prime in the polynomial differentiation operator such that, you know, L is equal to d minus alpha times L prime. I might have had some conditions. Okay, yeah, I mean, the thing is, to make this interesting, you would like for the order of the operator L to be higher order than 1. Of course, when the order of L is 1, that forces L prime to just be a multiplication operator by number, just a constant operator, right? So you put these two things, put theorem 5.1 and 5.2 together, what do you got?
Differential operators are commutative.
Well, that'd be a funny consequence since we used it proving it. It's oftentimes the case that, you know, if you have a theorem, then a corollary to the theorem will be like things you use to prove the theorem, right? But I think it's just this, that given L in the polynomials over the, you know, this differentiation operator, right? Then L is equal to d minus alpha L prime for some L prime in the differentiation, polynomials in the differentiation operator, if and only if what? If and only if L of e to the alpha zeta equal to 0. Now this is actually, I was actually very happy with this when we first found this for a reason that you might